Welcome back to the Explainer. So, if you caught our previous analysis, you know we left off with a single, kind of humble prototype back in 1989. Well, get ready because we are about to dive straight into this next chapter. And honestly, what happens next is nothing short of a breathtaking 12-year sprint of maritime innovation. We are looking at an incredibly rapid evolution, literally going from the very first icebreaker application straight through to those massive passenger cruise ships that dominate the seas today. Now you might be wondering, how in the world did a simple 1.5 megawatt prototype, the Silly, completely transform the propulsion of massive floating cities in just a few short years? You know, the marine industry is famously conservative. They don't just change up critical propulsion systems overnight. And yet, the rapid adoption and evolution of this podded drive system completely breaks all the rules of traditional maritime engineering timelines. It's wild.
We're talking warp speed here. The timeline just takes off right from that 1989 Sicily prototype, and it brilliantly illustrates the core span of what we call the sprint of innovation. By 1994, boom, we see the first actual commercial icebreaker installation. By 1995, we hit the passenger cruise ship breakthrough. And then, by 2001, the very first tackless installation is put into the water. In the heavy industrial world, moving a totally new concept through that many operational milestones in roughly a decade, that is an astonishingly fast rate of adoption. So let's break down exactly how they pulled this off.
Now, what's really interesting about this is the staggering, direct contrast between two consecutive years. Take 1994. The technology was applied to the Rothelstein icebreaker. It used two pods, and they were each rated at 560 kilowatts. Makes total sense, right? Icebreakers inspired the whole concept to begin with. But then, consider 1995. Literally just 1 year later. The Elation, this massive passenger cruise vessel, adopts the exact same underlying technology, but it uses two pods rated at a massive 14 megawatts each.
Yeah, you heard that right, 14 megawatts. We're talking a jump from 560 kilowatts to 14 megawatts in a single year. To put that into perspective, scaling up hardware of this immense physical size and electrical complexity usually takes decades of careful, iterative stepping stones. This massive power jump absolutely shocked the industry. It proved once and for all that the fundamental engineering of the pod wasn't just some niche tool for icebreaking. No way. It was the absolute future of high-tonnage passenger transport. So, once they nailed that massive power jump, the engineering focus naturally shifted from raw scaling to physical refinement. Let's fast forward a bit to 1998 and 1999 and see how this builds out. In 1998, the vessel Europa introduced the first mounting block, and crucially, the very first pod with a steering fin for way better hydrodynamic control. Then, in 1999, the Voyager of the Seas pushed the envelope even further. They installed three 14-megawatt units, and they introduced something totally brand new to the layout, the fixie pod. Okay, let's demystify some jargon here. What exactly is a fixie pod? Basically, it's a fixed, non-rotating pod unit. It gets installed right alongside the fully azimuthing, or, fully rotating pods. Its sole purpose in life is just to provide massive forward thrust with zero steering capability. So by combining two fully rotating steering pods with one fixie pod right in the center, a huge ship like the Voyager of the Seas gets this ultimate combination of raw pushing power and total precision maneuverability. It's kind of the best of both worlds.
Right around the turn of the millennium, the technology takes another huge step. In the year 2000, the compact Azipod launched as a standard product. Up until this point, remember, these were massive, totally custom-engineered solutions for specific one-off mega projects. The compact launch completely transitioned the tech into a standardized, off-the-shelf product for lower power requirements. It was a real game changer because it made this revolutionary propulsion available to a much wider range of everyday vessels, like ferries and research ships.
Which brings us to 2001 and a major evolutionary leap on the offshore supply vessel, the UT-745 Normand rover. This wasn't just the very first installation of the compact system. It marked a massive, high-tech software victory. The Normand rover achieved the very first techless installation. See, the hardware had been perfected in the 90s, but the 2000s, that era, was all about making the software brains behind the brawn even smarter.
So what does tackless actually mean for us here? A tackless installation means that the motor's RPM control is handled entirely through the electrical drive's own internal mathematical estimation. It requires absolutely no physical speed sensor, so no tachometer, mounted on the spinning shaft itself. And think about why that's huge. Eliminating a physical sensor that has to operate in a harsh, vibrating, underwater marine environment removes a major point of mechanical failure. It literally revolutionized how offshore vessels operate and maintain their drives. All right, quick check. Are you with me? Which milestone represents the very first time the RPM was controlled without any physical speed sensor on the shaft? Think back to that big transition we just talked about, moving from the 90s hardware boom to the software smarts of the early 2000s.
Got your answer? It's the 2001 UT-745 Normand rover installation, of course. This specific milestone was absolutely crucial because it proved that the internal estimation algorithms of those frequency converters were finally fast and reliable enough to handle the chaotic heavy load dynamics of marine propulsion, all without actually needing a physical set of eyes on the shaft. Let's just take a step back for a second and look at the sheer speed of this journey. We started with a spark of an idea and a patent in 1987. By 1989, that 1.5 megawatt Sealy prototype hit the water. 1995 saw the incredible 14 megawatt Elation breakthrough. 1998 gave us steering fins, 1999 brought us the Voyager's FixiePod layout, and that 2000 standard launch perfectly set up the Tacola's Normand rover in 2001. You came into this explainer only knowing an icebreaker inspired it, and now you can see this seamless, relentless timeline of innovation that completely rewrote the rulebook.
So why does this 12-year sprint matter so much to us? Because it perfectly illustrates how modern engineering triumphs actually happen. It required ridiculously rapid physical power scaling, jumping from kilowatts straight to megawatts. It demanded expansion across entirely different ship types, from rugged icebreakers to luxurious passenger cruises. It involved physical, hydrodynamic refinements like those steering fins and FixiePods we talked about. And finally, it was crowned by massive software leaps, like tacholess RPM control. It's the perfect story of hardware scaling and software smarts combining to create the ultimate propulsion system.
I want to leave you with a provocative thought as we wrap up today's explainer. If marine propulsion scaled this incredibly fast in a single decade, literally going from a radical sketch on an icebreaker's stern to powering the largest passenger ships ever built, what's going to power the ships of tomorrow? Just take a moment to be in awe of that maritime engineering. Now that you know exactly how this technology evolved, the next step is learning the language you'll actually use to operate it. Next time, we're going to step right onto the bridge and dive into the core operational terminology you need to drive one of these beasts. See you then.